Up to now we studied the steady flow energy equation, or the flow which we considered is a steady flow, right, in which there is no change in property with respect to time at a given section, right. So we can just derive the steady flow energy equation, which we can say is the first law of thermodynamics for an open system, which is your H1 plus V1 square upon 2 plus GZ1 plus Q is equal to H2 plus V2 square by 2 plus GZ2 plus WCV. This is all about your steady flow, when the flow is steady. Now we are moving towards our unsteady state flow. When the flow is unsteady, means the flow properties will change with respect to time at a given section. At one section, in different times, the property of flow, that is your pressure, temperature, velocity, each of this property will change at one section in times, right, with respect to time. So that kind of a flow is known as your unsteady flow. So we have to now study what happened in the unsteady state of a flow. So if there is an unsteady state of a flow, if I am talking about this control volume, suppose this is our control volume. This is a jar is there, this is one container is there, this is the inlet point, this is the outlet point, right. From here fluid is coming inside the system, from here fluid is going outside the system. With the help of this red line, we demarcate system and surrounding. So this red line is our control volume, or you can say boundary. So this is an open flow system when mass is transferred and energy is transferred. Now if the flow is unsteady, there can be two things which is possible inside this system. Because of mass transfer, mass can change, and because of energy transfer, energy can change. In case of a steady flow, we already studied that the flow is steady if there is no accumulation of mass in the control volume. Means the mass of the control volume will not change. The initial mass of the control volume will be equal to the final mass of the control volume, or you can say the mass flow rate at the inlet is equal to mass flow rate at the outlet, so that the net mass of the control volume will remain same. This is the case of steady flow. If the flow is unsteady, so in unsteady flow, there is some amount of mass or some amount of change will happen in this control volume, or we can say that the rate of change of mass dm by dt of a control volume is not equal to 0. There may be a case if inlet mass is more and outlet mass is less, so some mass will remain in this system, or if inlet mass is less and outlet mass is high, then some of the mass which is already present in the system will go with will decrease, right. So in a control volume or in a unsteady state flow, the dm by dt, or the rate of change of mass of a control volume, is not equal to 0, and it is equal to, if we are saying that the rate of change of control volume mass will be equal to the difference between your mass flow rate at inlet and mass flow rate at outlet, right. Suppose this is your 100 units of mass is coming in and 60 unit of mass is going out. So we can say that the rate of change of control volume mass will be 40, right. 100 is coming, 60 is going, remaining is 40. So 40 is the rate of change of mass of a control volume. So in the case of your unsteady state, the dm by dt of control volume is not equal to 0. It will be some value is there. Also, second is there can be an energy transfer, right. When the flow is coming inside, this fluid is coming inside, it will bring some energy. That energy is because of temperature, internal energy, it is coming. Because of flow work is there, some velocity is there, then kinetic energy. At some height, this system is at some height, then it has some potential energy, and we are assuming that some amount of heat, that is Q, some amount of heat is added to the system. So we can say the energy which is coming inside the system is internal energy at the inlet because of temperature, flow work, because of velocity v1, some kinetic energy, because of some height, some potential energy, and we are giving some heat. So this Q, this is the energy at inlet. When this fluid is going out of the system, it will take some of the energy along with it. That is, it comes out with some temperature, say T2. Corresponding that T2, some internal energy U2 is there. That flow is there, so flow work it will take, that is P2 V2, with V2 is the specific volume. With the some velocity it is going out, so that is V2. So corresponds to V2, there is some kinetic energy, and because of some height there is some potential energy, and we are saying that this system is doing some work on the surrounding, that is W. W is the work done by this control volume or by this system on the surrounding. So this much amount of energy is going out of the system. U2 plus flow work P2 V2 plus V square by 2, that is kinetic energy, plus GZ2 because of some height, plus some work WCV. This is the amount of heat which is going out of the system. So in steady state, we are saying that the energy which is coming inside must be equal to the energy which is going out to maintain the steady state of this control volume, so that there should not be any change in the energy of control volume with respect to time. But now our topic is your unsteady state flow. So in unsteady, the rate of change of energy with respect to time of a control volume is not equal to 0. Means energy coming in is not equal to energy going out. There must be some accumulation of energy inside this control volume. So this is the unsteady state. So we are going to derive the equations for the unsteady state, how we can move in the questions, how we can do. So I am assuming, let m.1 is the mass flow rate of fluid which is entering from the inside the system, and m.2 is the mass flow rate which is going out of the system. So first equation what we are saying is conservation of mass. Mass is conserved, right? We are saying that conservation of mass says that the rate of change of mass with respect to time of this control volume is equal to rate of mass coming inside minus rate of mass going out of the system. So this is the conservation of mass, saying that dm by dt of a control volume will be equal to mass flow rate at inlet minus mass flow rate at outlet, right? Because the net mass will be conserved. So we can say that mass which is coming inside the system, suppose 100, out of this 100, 40 will remain in this system and 60 will go out. So this 100 will be equal to 40 plus 60. Mass which is coming in is equal to mass which is accumulated here plus mass which is going out. This is the conservation of mass. So this is the conservation of mass equation. dm by dt of a control volume is equal to mass flow rate at inlet minus mass flow rate at outlet. What is this? This is rate of change of mass of a control volume, right? Change of mass of control volume means I'm writing the final mass of control volume minus initial mass of control volume. When this process will start working, when this flow will start, suppose initially when we make this system, initially some mass is there, right? So we can say that the rate of the change of mass is final mass minus initial mass. So the final mass minus initial mass of a control volume divided by time dt is equal to mass inlet minus mass outlet, right? So we are taking this equation in our numerical like this only, just because if we simplify this equation, so this is very easy to make in our numericals. final mass of a control volume minus initial mass of a control volume divided by time dt is equal to mass inlet minus mass outlet. This is our first equation, that is conservation of mass. Now second one is your conservation of energy. That energy is also conserved. We know energy is conserved. The amount of energy which is coming inside is equal to amount of energy which is accumulated in this space plus amount of energy which is going out, right? So we are saying that suppose E1 is the energy entering into the control volume. I am taking E1 is the energy entering into the control volume and E2 is energy leaving the control volume, right? From here energy is leaving is E2, from here energy is entering is E1. So E dot 1, this is rate of energy, right? With respect to time, we are more focusing upon time because this is a continuous process. So E dot 1 is equal to, what is the energy coming inside? Energy coming inside is because of temperature, internal energy, because of velocity, kinetic energy, because of potential energy, because of height, potential energy, because of flow, this flow, some flow work and some heat is also entering into the system. So I am writing energy entering into the system is m dot 1, this is the mass flow rate at the inlet, into h1 plus v1 square upon 2 plus gz1, right? This is the amount of energy which is coming inside the system plus q, you are adding some heat into the system. Just make one thing very clear, in steady flow energy equation we are writing the equation without m dot 1, right? Without m dot 1, right? In steady flow energy equation what we are writing is this equation h1 plus v1 square upon 2 plus gz1 plus q. There is no mass terms in that steady flow energy equation. So I told you there that this q is heat added per unit mass, right? That heat, that unit of this q must be kilojoule per kg if we are using that steady flow energy equation. Now in this we are writing m dot 1 here, m dot 1 here. So this is the energy per unit mass, multiply by mass, this is your energy rate. The unit of this is your kilojoule per second because of time, m dot is per unit time. So the unit of this term is kilojoule per second. So the unit of this q must be in kilojoule per second. So please remember, in steady flow energy equation the unit of this q which we are taking is kilojoule per kg second, and here you have to take the complete q, you need not to divide this q with mass, right? The unit of this q must be in kilojoule only, right? In steady flow it is kilojoule per kg because I am multiplying by mass here. So this is the energy at the inlet, m dot 1 into h1 plus v1 square upon 2 plus gz1 plus q. And energy at the outlet, energy going out of the system is mass flow rate is m dot 2 into, because of some temperature, some internal energy is there, velocity is there, then some kinetic energy, because of some height, potential energy, because of some flow work, this flow energy, and system is doing some work on the surrounding. Work is done by the system, so some energy is transferring in the form of this work. From the system, some amount of work is going out, so it will take some of the energy. So we are writing energy out of the system is m dot 2 into h2 plus v2 square by 2 plus gz2 potential energy plus wcv, which is work done by the control volume on the surrounding. Same here, the unit of this wcv will be kilojoule, not kilojoule per kg as we see in your steady flow energy equation. I am multiplying here with mass. In steady flow this mass term is not there, then the unit will be of Q and WCV will be kilojoule per kg. You need to remember this thing. Now, conservation of energy says the rate of change of energy of control volume. The rate of change of this energy of control volume will be equal to rate of change of energy at inlet minus rate of change of energy at outlet, right? The energy which is coming inside the system will be equal to energy accumulated here plus energy going out of the system. Conservation of energy will be applicable here also. So this is dE by dt of a control volume is equal to dE1 by dt minus dE2 by dt. If I simplify, if I put E1 and E2 value here, so this is d by dt of E1 is m dot 1 h1 plus m dot 1 v1 square by 2 plus m dot into gz1 plus q minus d by dt of E2, E2 is m dot 2 into h2 plus m dot 2 into v2 square by 2 plus m dot 2 into gz2 plus wcv, right? Units, you need to take care of about units, right? This is the conservation of energy. And if I am saying that if I assume that changes in kinetic energy and potential energy of a system, changes in kinetic energy and potential energy of the system is neglected, then we can write, if changes in kinetic energy and potential energy is neglected, so we already studied that E can be replaced with U, internal energy, right? Why internal energy? Because then the system is stationary system. So in place of E I am writing U. This is du by dt of a control volume is equal to d by dt of m dot h1 v1 square z1 terms will goes d by dt of m dot 1 h1 plus q dot, that is your heat transfer rate, minus d by dt into m dot 2 h2 minus wcv dot, that is work transfer rate. Or if I simplify it, this will be equal to d by dt of, this is of control volume. So change of internal energy of control volume is U final minus U initial, U final minus U initial of a control volume, right? Just remember one thing, these terms are your multiplied by mass. So this is not small u, this is not specific internal energy, it is internal energy, right? The unit of this will be kilojoule, not kilojoule per kg. So unit you need to take care. This is the final energy, final internal energy of a control volume minus initial internal energy of a control volume is equal to the same term d by dt into m dot 1 h1 plus q dot minus d by dt into m dot 2 h2 minus w dot cv, right? This is the second equation, that is conservation of energy. So in question we will go like this only. First we'll apply conservation of mass, then we'll apply conservation of energy. In textbook you will see some of the more simplified form of this unsteady flow equation, but we are only go with this concept. First conservation of energy, second conservation of mass, right? Further simplification will add some more assumption. So we will not stick with the assumptions. You need not to learn the assumptions, right? These are the basic. These equations can apply to any question or anything, any process, any system. So we are not again simplifying it to make some more assumptions. So we will stick to the equation of conservation of mass and conservation of energy.